Hello, good afternoon. Hope you all are having a good Sunday. You may notice I have switched up my camera position. It's a little bit more on my face now. I have my streaming software off to the right. So if you may see me look off that direction, that's why. But I'm happy to be back streaming. And I hope we're going to have a good stream this afternoon. Excuse me. Why don't we get started? I don't see anybody in the chat yet, but as soon as you join, please let me know. In the meantime, I might retweet my post from earlier, and maybe we can get. Hi, John. A long time no see. How are you doing? I hope you're doing well. Yeah, I miss North Carolina. That was some of the best years of my life were there. So thanks for joining. We're gonna do something a little bit different today. Over the last 4 or 5 months, I've been doing game development with Bevy engine. Not real sophisticated game development. I'm kind of a newbie to it. But today I wanted to do something that was more in my wheelhouse. And maybe we can get if we're lucky, we can get 2 implementations. So my goal is to do some follow this tutorial that I've been wanting to follow for a while. And it's about implementing Berkeley DB. So Berkeley DB is a very old format at this point. I think actually there was some award that the creators of Berkeley DB won in ACM or something like IEEE, I forget. But they got honored for it because it's a really influential technology. It's basically like the guts of a database. And it says DB on it, but it's more like a key value stored that's built on top of a B tree. And now the modern Berkeley DB software is much more sophisticated than that and has a lot of things in it that are useful for more general applications. You'll see it used by some things that ship with Linux or with other operating systems. So it's pretty ubiquitous. I think technically Oracle owns the patents on it nowadays. So let me finish reposting my stuff and we'll get started. Okay. All right. So, yeah. Okay. Here we go. So this is the blog post. I'll paste the link in the chat if it'll let me paste. There we go. And so we're going to start with the first post here. I say it's a post series implementing Berkeley DB. Now it's obviously not complete. They've done some of reading. I'm not sure if there's more to do with reads. There might be scans as opposed to point reads as well. And they haven't done writing and recovery. But we can get pretty far. So we're going to start with implementing the page format. And I don't know about you, but I love these kinds of diagrams. This is great. If you've ever tried to implement a protocol and you looked up the RFC, they have diagrams like this. Now, I think these are actual bytes or bits. Yeah, bytes. Sometimes the diagrams in IETF are like words, so like 4-byte or 8-byte words. But we'll figure out by going through this post what we need to look for. Hi, Isaac. Welcome back to the stream. Good to see you. Okay, so we're going to start with the page format, and I have made a little BDB tutorial directory. And what I want to do, rather than directly starting from the top, we're going to start at the bottom, because each of these posts has a task, like, did you create a compatible implementation? So we're going to do this first, and then that way we can check if our output looks something like what the output they're expecting there. So let's just copy this, gendata.py. Okay, I should have used pd paste there. And let's make that executable. Now I went to look on Homebrew about whether Berkeley DB was in Homebrew, and it is. However, it's what do they call, keg only. It ships with Mac OS, and it probably ships with your Linux installation if you're running Linux, because it's used by so many things. So I shouldn't have to. Let's just see what this does. Okay, so it prints out a bunch of stuff, right? Let's do db load, as they say, btree test data.bdb, and yeah, so that's like 40 blocks. Okay, so about 20K. Okay, cool. So now that we have our test database created, let's go back and start a project, and we'll start reading this format. Okay, so I'm going to make a new, and I think we're going to have to do a binary, and it's going to do very little, I think. Yeah, let's just say BDBRS. We're going to call it that. And we'll go back, if we have time, we'll go back and do it in Elixir as well, because I think that there are some things about these sorts of problems that Elixir's binary pattern matching is really good at. So let's have a look here. Okay, and we're going to open this directory. Okay, and I'm very sorry, I forgot to put the settings down to smaller. I think it was 11 and 10. Yeah. Oh yeah, UI font size. Oops. There we go. Okay, that's a bit more reasonable for stream. Okay, so our main program here, we will probably start with stuff in here, and then we'll make the part of the later posts in this are about making a compatible ABI. I don't think that that's necessarily what we want to do, because there's all of the extern C goop that you have to do in Rust to make that possible. I'm not particularly interested in that. And like possibly having some unsafe code to represent structs we want to have in Rust as C pointers, and then like I just kind of don't want to mess with that right now. We might just make something that looks a bit like it if we get that far. But let's start with just the reading the format. Okay, so what I'm going to do here, we're going to take, excuse me, let's use standard FS star for now. Yeah. And we're going to need, not Python, standard env, I think has args in it. Yep. Okay. And what can we do with this? Oh, it's just an iterator, right? Does it implement index? It does not. Okay. You can tell it's been a while since I've done some Rust. Okay. env. So let's do let args equals env args. Let's actually file name next. And since this is just a test program, we're just going to unwrap. So we want to get the file name out of the args. Now this is going to be, it's going to come out as a string, so we're okay there. And let's get, this is not, you know, we're just going to get something to work, right? I don't want to make this scalable at this point. What we're going to do is just read the contents of the file. And maybe I'll just do like this. fs read. I don't want to read to string. Okay. Yeah, so we're going to read file name and unwrap that. So that should, yeah, reads it into a vector of bytes, which is what we want. Okay, so let's look at this. So the first page in any Berkeley database is a metadata page. So this is the, so there's this LSN, which we'll find out. The page number, I'm guessing, a magic. So this is going to be a marker type of field. Version, page size, looks like some flags. Free, I'm guessing it's a free count or a pointer to the first free entry. Last page number, number of parts, key count, record count, flags, UID, etc. Okay, so we're going to learn what these are. So the magic number should always be 53162. So that's in hex. That's interesting. So that should be 3 bytes. So it's 053162. Okay. So let's, maybe we could do some of this with nom, but maybe we want to try to map this, like use repr-c on a struct and try to map it into the struct. Let's see what we can do. Okay, so free list page number, this will be used once mutations are implemented in the tree. We're not concerned with that yet. The page number of the last page in the database is this 30. So last page number 32 to 35. So 20 in hex. Okay, so this can be used instead of relying on size of database file divided by 4 kilobytes minus 1. Okay. And then root. The page number of the root of the B tree, reads of the B tree should start from this page. Okay. This gap, the gap resumes on byte 460. So the entire structure is 512 bytes inside. So maybe what we can do is let's, since this is a vec of U8s, right? Let's get the metadata page. Let's say metadata contents, and let's take contents 0.512. So that'll give us the first 512 bytes. And let's see here. Okay, I'm going to go ahead and make a struct metadata. and we'll start filling this in. So this is 8 bytes. So that's like a U64, I'm guessing. Page number is going to be 4 bytes. So it's a U32. Magic. We don't need to fill that in. I think there's a question here about whether we want to try to interpret the bytes directly onto this struct, which is going to require some unsafe code probably. Maybe we just leave out the magic. So no magic here. Version is another U32. Page size is a number U32. Those are each 1 byte, so TY, U8, MF, U8. We don't have anything here. Empty byte. Free list page number, so that's U32. Last page no is another U32. And parts, another U32. Key count. So you can see it's really just giving us this is interesting. That's 3 words. I think we will need a U128 to fit that. Yeah. So what I wanted to do here is make a really simple, maybe we'll make a constructor for metadata, and it will fill in all of these things for us. So yeah, let's say UID U128. Oh, I'm sorry. So that spans, I don't know what that is interesting. It spans 5 bytes. Maybe we treat this as a vec U8. And then we don't care about what the contents of it, interpreting what the contents of it are. Now we could, I'm not sure about this yet, we could potentially try to avoid copying here. So let's go ahead and put a tick A here, and maybe we do, this is a slice of U8s, and then we get, we get the 5 words or whatever. Okay, and then there's a skipped field, empty word. And I'm saying word because I'm pretty sure that this Berkeley DB was originally written for 32-bit machines. So, 4 bytes, 32 bits would be a word. Okay, min key. I'm just going to have to assume that that's pad. I guess we'll find out what this I is. Okay, so the checksum comes at the end. RE pad is a U32 root. So it talks about root. The page number of the root of the B tree, reads of the B tree should start from this page. Okay. Okay, so let's do yeah, I guess we need to do, let's do implement metadata and see if we can do without. And here we're going to take a slice of U8, and then we're going to return, and this is generic over this. Okay, that's what's going on here. Oh, I need a type here. So this is a buffer. Expected an item. Okay, so that's fine. Yeah, maybe we can do this and remove the annotations here. Just say self. Let's see if it'll. Okay, so now it's just complaining about I'm not returning the right type, which is what I would expect. Okay, so we don't need to annotate that specifically. Okay. So the hard part is we need to make sure that this magic number is okay. And maybe what we should do is something like you know, this is a slice of U8s. I kind of want to bail if I wasn't given at least 512 bytes, right? So, and here, we're going to do something here. We're going to derive, debug, clone. I don't think we need to derive equal, partial, equal. We'll start with that. Okay, so we want to read. So we're gonna just start to read these off. Let's panic. Say if buffer length less than 512, panic invalid metadata page. Okay, so we just validated that. Now we could use results and stuff. Maybe we'll go back and do that later. Probably best to use results in this sort of situation if you're building a library, right? Okay, so let's read the magic. So maybe we say if let magic for, yeah. Maybe not if let. I say if buffer. So this would be, you're saying 12, 15. Is that going to give me 3 bytes or 4 bytes? All right. Let's try U32 from BE bytes. And then we give it a slice. Borrowed slice. Let's see, not equal 53162. Panic. Valid magic. Metadata page magic. Meet data. Okay, what's wrong here? Expected U8-4 found a slice of U8. Okay. That's interesting. Let's look up that documentation. U32 from B bytes. Okay, so we can use a fallible conversion. Dot try into dot unwrap. And let's remove the slice. Here, okay. Split at. Yeah, that's not exactly what we want to do. We don't want to split it. Oh, and it should be LE bytes. I don't know why I was using big endian. Probably habit for running network stuff. Okay, so what's wrong here? Let's pull out the conversion. Let magic is that. And then say if magic is not equal to if maybe missing an else. Oh yeah, it's just complaining about my return value. Okay, so we have validated that we're getting the magic. Okay, and let's maybe implement default. This probably is not going to work. Or maybe it's just an empty slice. All right, so we're probably going to have to do a lot of this stuff, which is okay. Okay, so now if we validated the magic, we can do from LE bytes. And I think that this is wrong. It needs to be 12 to 16, non-inclusive, right? Because this will be 0 to, this will be U64, 0 to 8. So 8 being the upper bound. Try into unwrap. It's weird that I don't have, or that I have to use the fallible version. There's no infallible version that panics. Okay. And we're just going to do this for the rest of them. From LE bytes. 812. You can see this might get a little bit repetitive here. Now we could potentially skip some of these things until we actually know we need them. Let's look at their output down here, see what they print. Okay, so they're printing out everything. Actually, they're skipping those little fields. What is this meta flag? Oh, those are just flags? That's interesting. Okay, so they're printing the UID as a big number. Maybe what we'll do later is oh, that's interesting. So they include the stuff at the end of the file in this structure. So maybe this assumption that like it needs to be 512 bytes is not sufficient. So if this is 5 times 64, we got 320 bytes at the start of this line. So that's 324, 328, 342. And then there's this. And it's not clear what this I is yet. Okay, so yeah, they say all fields are in host byte order, so almost certainly little endian. What I would like this UID to be, or rather to print out as, is the hex representation of those bytes. So we might need something that can just loop through this slice, and just print out each byte as a hex, 2-digit hex number. Okay. Meta page. So yeah, we need to know where this I comes from. Okay. But let's go ahead and get the rest of these fields, and then we can create the struct, and we can maybe move on to the next thing. Let's go ahead and put these things in there. Checksum is also a slice, because we can't fit that in a normal type. Now we could do something like, say this is an array, because we know the size of it. That would be potentially better for UID, just for safety as well, because we know it has to be 5 words. But I'm not so sure about that right now. Okay. So magic number. Okay. Free list page number. Let's start to get. I'm gonna leave these things out for now. It doesn't look like they're using them down below in their output. Maybe we can capture the magic. Okay, so LSN page number magic version. Yeah, I'm just gonna copy these things. So version is going to be at byte 16 to 20. Page size. Make sure to use the same variable name as the field. That'll save us some time later. 20 to 24. And then we're going to skip the next one. So free is going to be, so if that was 24, this will be 28, 28 to 32. And do it again. Last page, no. Okay, and this is going to be 32 to 36. And parts, sorry. Now I'm pretty certain there's out there some crates that will kind of automate this for you. I am just not doing it right now. Part of the fun, I guess. Okay, so key count 40 to 44, record count is going to be 44 to 48. Okay, flags. Oops. And that's going to be 48 to 52. All right, and now we've got our UID. So our UID is going to be buffer 52. That 5 times 32 would be, sorry, not 5 times 32. 5 times 4 would be 20, so we're going to go to 72. Does that sound right? So this would be 64, right? 68, 72. Yep. Okay. And then we skip one, and we're going to do min key is going to be something like this. Let's see if they say what min key is. Yeah, min key is a number as well. So they're treating it all as a number. That's fine. So min key, this is 64, 68, 72, 76. $76 to 80. Yeah. Okay. And len is this. Do 80 to 84. Yeah, again, this is very mechanical. I'm sorry for it being a little bit boring, but we're near the end here. Okay, and then we're going to say root is this, and it is 88 to 92. Okay, so now we have all the fields except for these. And I don't know what we'll fill in for checksum, but let's go ahead and fill the struct fields. Okay, so now we need to do crypto magic. We need to figure that out. Let's leave it to do here. Actually, for now, let's just put 0. And IV, let's just put 0. And checksum, let's just slice the buffer, an empty slice of the buffer. Okay, so now it's like, hey, this is where we're going to get into the problems. Okay, that should solve that. Okay, so we did not make a field for REPAD, did we? We did not. All right, REPAD. And we're missing REPAD down here. Okay, so now since we have implemented debug, let's go ahead and metadata, new metadata contents. Okay, and this is our entire main. This needs to be a borrow. And then this does not. Okay. So let's look at this again, and then maybe we can print out that metadata page. Okay, so we're taking a file name off of the command line. Yeah, no kidding, Isaac. Thank you. That struct unpack would be really nice. Actually, Ruby has one as well. I forget what it's called, but it's similar. Yeah. In Elixir, this would be just freaking easy. We just make one big pattern, and then there's all our variables. Okay, so we're reading the file name off the command line. We're reading the entire contents of the file. Luckily, this file we just created is only 20K, so I'm not worried about it. Then we slice off the metadata. So this is the contents of the metadata, needs to be 512 bytes. And then we call metadata new, and then we're just going to we're just going to debug that. Now this is, let's see, we can build it. Yeah, I know. Why do I have 3 of these? I think it was the work I was doing the other day that required me to have 3. It's just complaining about these fields are never read. Probably because this debug macro doesn't. Let's do print line. Metadata. Then they might count as read. And it's still. Okay. So let's do cargo run, and then we're going to take that test data.bdb as the input and see what we get. Haha, we panicked. Okay. Invalid metadata page magic. Okay. Do I have a hex editor? Hex dump. Okay, so here is that magic, right? Interesting. Yeah, so that's little endian, sort of. Did we do that wrong? Did we do BE bytes by accident? Or did we slice the wrong thing? Let's do print the magic. See what it says. And then what's the format? Formatting syntax. Okay, so that'll print. Print the debug formatting. $X. I don't need to specify how many. Let's just do it. Let's see if that works. Okay, so it thinks it's 02. So I think we sliced the wrong thing. So let's look at this again. So C, A is 10, 11. C would be 12, right? Oh, well, it helps if I do that. If I type the right number. Okay. Okay, it's still producing the wrong. So it's only getting the 2. 053162. So like if it's the full, right? If it's the full 4 bytes, it should be 00. This is after treating it as little endian. Let's look at the hex dump again. Okay. 4 bytes. So this is 2 bytes, 2 bytes. So that's the first word of the LSN. And then we have, why does that look like middle endian to me? Obviously, page number is going to come out 0, right? Regardless. But what's interesting here is this. Why did I say middle endian? Because these are switched. I wonder if this is just an error in his blog post, because sure, you take this and make it the most significant digits over this, but it's byte order, not like nibble order. Not nibble, that's not what I mean. It's byte order. It's not, 16-bit order. Unless it is, unless that is the definition of the file format. Okay, I think for now, because we know that this program produced the right stuff, because it's used by the operating system, like we're making new code here against a reference implementation. So I think what I want to do is go, this is 6231, not 3162. I kind of don't want to make that assumption based on this, but like this just seems wrong, because you should read left to right in the byte order, not right to left, or not, big little shift big little, right? That doesn't seem right. Okay, so let's run again. Okay, it's still reading the wrong stuff. So, oh, it helps if I save it. Okay, it still thinks it's 2. Yeah. Okay. Oh, interesting. The rest of the 4096 byte page is unspecified and unused. Okay, so they're doing 4K pages, which makes sense. Yeah. Okay. 8 to 12. Okay. I kind of want to put that back. It just, I wonder if there's some option to hex dump that I'm missing. Let's see. Display the offset in hexadecimal probably 16 instead of 2. Let's do -x. I don't know if that improves anything, but if anyone has any ideas here, that would be helpful. Otherwise, I'm just going to treat this as a bug in the definition. Yeah, it's still not reading the correct number of bytes. Can you print with byte grouping? That's what I was trying to do on hex dump. So these are like the offsets. I don't need to care. I don't care about the offset. Hex stump dash capital C. Okay. I don't know. This is Mac. It may not have the same stuff. Let's try that. Thanks, Isaac. Okay, so yeah, here we go. Thank you, Isaac. That's really helpful. Okay, so it is 623105. So it was hexdump was regrouping those. So okay, so maybe the problem is that I'm not reading the right set of bytes. So 0, 1, 2, 3, 4, 5, 6, 7, right? 8, 9, 10, 11. So 12, 13, 14, 15. What if I try this? There may be some stuff too that's like... Let's pop this out. And then we're going to debug magic bytes. And then we'll pass it here. Because I want to see what is actually coming out of there. Oops. Okay, so we are getting 2. Two zero zero. Where is 2 in that output? In that file? I mean, there's a 2 there, but that's not it. How are we getting 2? Okay, I'm going to change this back to not inclusive. It helps my brain if they're on 4 multiples of 4. Maybe I can print the first bytes of the buffer. Yeah, let's do print line. I don't know if this is going to work. It's probably going to complain. Buffer 0.16. Yeah, it doesn't like that. Yeah, it's possible we're getting some stuff, something here we shouldn't. Let's do... So it's not a string. Maybe we can just do a debug. I'm doing this wrong. Pretty print the debug formatting. Okay. Actually, we just want to do question mark. Yeah. Okay. So that is really interesting. We are getting We are getting some weird stuff here. Yeah, where's that data coming from? That's an excellent question. What it's looking like to me is let's put let's put let's print something here before we pass it to our constructor. Because we're getting the wrong stuff in the file from the file, then that could be the source of our problem. Oh, that's weird. I wonder. So 207. Yeah, there's something going on here that we should not be seeing. But if we, this is really weird because if we hex dump the same file, we get what we expect. Right? So where is this? .207 coming from? Are we getting? Yeah, this is really weird. Okay, just for my sanity's sake, I'm gonna make a new file. Yes, I was hex dumping the same file. This is really bizarre. Okay, db load t b tree test data bdb. Okay, so now we have the test data right here. Okay, still getting the same problem. Hex dump C test data. Here, like head 10. We're going to start doing some stuff. Oh, you know what the problem is? Oh, I was hex dumping the Rust program. Because args. Yeah, I need another next. Here we'll do skip one. Oh my goodness. Or drop. What is the iterator method for that? Skip. Iterator. Oh my goodness. I wanted to say nth one. Oh my goodness. Oh man. Like, why is this not working? I'm reading the file, the wrong file. Okay. That was silly. That was silly. Okay. So now up here, yeah, we can remove some of this probably. Um, let's see how far we get now. Ugh. Oh, okay. So we got a metadata struct, and let's print it out with line breaks. So it prints out. Okay. So looking at their output, progress. Yay. Okay. So we got the same LSN as they did. Got the same page number. The magic, we should print that as hex. We can update the debug, you know, um, to print the right stuff. Okay. Version 9, page size 4096. And, oh, encrypt alg. Is that one of those fields? I don't see. Okay. They're not explaining what that is. Type. What's type? Is it TY? Okay, so we need these fields. They lied to us. Okay, so EC and TY and MF. Okay. So where is those that come after page size? EC is buffer 24. TY is buffer 25. MF is buffer 26. And then there's, yep, skipped byte 28. Okay. And after page size, EC, TY, MF. Okay. So, oops. Going down to their output. So encryption out 0, type 9, meta flags 0. They just renamed those. We can probably go back and rename them later if we want. Free, last page number is 4, number of parts is 0, key count 0, record count 0, flags is 0. I'm assuming this is similar. Min key is 2, RELen is 0, REPad they're doing is, yeah. Root is 1, crypto magic is 0, IV is 0. Now we hard coded those. What we're going to need to do is like get those off of the end, and which means we're going to have to pass an entire page. So let's do the first 4K, and here we're going to do that, and then let's look back up here, and they say, excuse me, rest of the 4096 byte page is unspecified and unused. So what's interesting is, I don't know what this, yeah, again, I don't know what this I, like, so 4096 should come out to a complete row, right? Because it would be a multiple of 16. Yep, 256 rows. So I'm not sure why this checksum doesn't, unless this is added on to the end. What does this mean? The gap resumes on byte 460. Because we figured this out. So that's 80, 84, 88, 92. 92 bytes. Why is there 460? Oh, well, they're saying, okay, I'm misunderstanding this. So we do want to pull this off, but they're saying at byte 460 is when crypto magic starts. And then it goes up to 512. So really they should have aligned this differently. Because it doesn't start at the beginning of, I mean, 460 divided by 16 is not, doesn't divide evenly. So, right? Yeah, so like that's 4 bytes below a boundary, a 16 byte boundary. Okay. So let me revert that. We want 512. We don't care what the rest of the page is, even though it's a whole page. And we might make a type alias later that is like a page, and it's a, if we can do a 0 copy conversion into that type or something. Anyway, let's, so I think now what we want to do is let's define crypto magic. And this is going to be U32, and it's basically like this, right? But it's going to be 460 to 464. Okay, we'll remove that. And then we can say the IV. So then they're saying 3 words are skipped. So we need to skip 12 bytes. So the IV then starts from there, and that's U28 from LE bytes. And we're going to do 12 bytes plus 464 is 478. And then it's 16 bytes long. Okay, we're gonna figure this out. 16 bytes, 478 plus 16, 494. And then the checksum. So let's get the IV in here, not as a dummy field. So then the checksum has to be from 494 to the end. Buffer 494, 512. And let's make sure that minus 494, 18. So that's not right. What did I do wrong? See, 4, 8, 16, 20, 24. Minus 24. 488. Where did my math go wrong? Okay, it resumes on 460 to 464. Maybe let's count backwards. So 512 minus 20. 512 minus 20. 492. So it needs to start at 492. I was off by 2. That's weird. Okay, and this ends at 492. And 492 minus 16 is 476. Okay. And then we need to subtract 12 bytes from that. 476 up. 476 minus 12. 464. Okay, so I just made an off by 2 error in there. All right, let's run this again and see what we get. Okay. It's complaining about all those. I might just make those pub, but whatever. Okay, so we're getting all the zeros. The crypto magic is 0. The IV is 0, as we expect from all this, because it was not encrypted, right? Okay. Cool. Maybe later we will implement debug. I think this is good enough for me right now. Okay, so that's page 0. Now it's saying the root is page 1. So let's look at what a B-tree page is. And we'll make a struct for that because we're going to need one. Right? Okay. A B-tree inner node and a B-tree leaf share the same header. They differ by what the entries in the page represent. So the rest of the so this is the header. So we're going to have an LSN again, U32. We're going to have to do some of the same stuff. Interestingly, probably in C, this was implemented as a union between these things, and then they just like, use different stuff for different. This is, sorry, U64. And previous page number is U32. Next page number is U32. Entries is U16. HF offset, I don't know what that is, but we'll find out. Is U16. Level is a U8, and type is a U8. And then there's a question here that needs to be TY because we can't use type as a name. There's a question here about whether it all starts here and flows on from there. But we're not trying to implement reads yet. Let's just say this is a B-tree page header. Okay, this is interesting. So previous page number says the leaf page containing lexicographically lower data. So this would be like if you're trying to scan backwards. Obviously, if we saw the hex dump there, and as well as the output of our metadata, the metadata page is always page 0, I'm guessing. And then the B-tree pages are 1 and beyond. So if this is 0, if there is none, or if it's an internal node. Okay. What we might do here. Okay, so we've got the metadata. We want to start from. We want to loop through all the pages and get their headers out and print them out, right? Okay, so we'll do some validation on some of this stuff. Because each one of these is going to be on a 4K block. That's what they mean by page. Okay, so we're about a bit over halfway through our stream. Let's go. It's nightly experimental. Is there just a chunks? Or is it just on slice? I don't want windows. Chunks is on slice. Okay. So chunks are slices and do not overlap. That's exactly what we want. Okay. So let's say for chunk in contents 4096 to the end, chunks of 4096. So let's give us individual pages. Now we're going to interpret each of these as a B-tree page header. So let's go ahead and make that new. Okay, and then we're going to take, this is going to be a page, and this is going to be a slice of U8s, and return self. Okay, and we're going to do some of the same things we did up above in the metadata. So let's copy some of this. So again, we know that that's 0 to 8. And page no, it comes right after that. And then we'll do something similar for previous page number. Previous page number. That's going to be 12 to 16. Next page number is 16 to 20. Okay. Entries is, oops, it's U16. And that's going to be 20 to 22. HF offset is going to be that, but 22 to 24. Oops. We need a range there. Okay, and then level is going to be buffer 24, and TY is going to be buffer 25. And here we need to leaf node is 1 and it counts up, so yeah, that makes sense. It builds the leaf nodes first, and then as the tree grows it adds internal nodes. Okay. Page type, DB meta page is type 9. Internal. Okay, so what we want to make sure is that only 9, 3, and 5 are valid here on TY. Okay. If TY is 9, TY is 3, TY is 5, we're going to panic and say invalid page type, and we'll print it. Okay, otherwise we're going to do self, fill struct fields. And then we've got, so this I need to rename to entries, right? And there we've got the page header. Okay, we're going to rename that symbol to page. Will you rename it for me? Here, buffer. And then can we rename that whole thing? Please, Zed, work for me. Page. Okay. And chunks. Okay, and then let's complain about unused. And the other thing we need to do here is probably if page.len 4096, and we're going to panic invalid page size. Okay. That's not strictly necessary, but let's do it anyway. Okay, so we're going to say btree page header new and pass it chunk. We'll say let header. And then we're going to be print line header with debug and line breaks. Okay, and this should get us, what's wrong here? Oh yeah, we need to derive debug on this. And clone, we possibly don't need clone, but okay, that's pretty good. Let's run it again. Okay, so we've got the metadata page. Which we had before. And then we have page 1, which is all the same 3 entries. Level 2, so that's 1 level above the leaf. And is type 3, which they say is an internal node. Okay, so that's what we expect if it's above level 1. And then here's page 2. Previous page number is 0, so this is the first page in the leaf. Next page number is 3, right? So 2, 3, etc. There's 24 entries. I don't know what HF offset. We'll learn about that later. Level 1, type 5, so that's a leaf node. Okay, so we're getting there. We're getting the right stuff now. This is good. And we're getting the all the same stuff. So let's read about what this high free byte page offset. The space between this byte offset and the header is empty. I wonder what that means. Is it saying you need to scan this many bytes before you can read something? I wonder if the items come at the end of the page rather than the beginning of the page. Interesting. Well, so for an internal node, let's look at how many bytes this is. This is, oh no, an internal node would still have entries. It would just be like the keys or something. I guess we'll look at that in a future exercise. But like, that's, 300 bytes off of the page size, right? Which is kind of interesting. Of course, the header is only, 20, 24, 20, 26 bytes long. So I don't know if that means anything. Okay, cool. So we got something pretty similar to this. We can make it look like this. I don't think that's really important right now. Maybe we just go to the next exercise? Okay. So our next goal is to be able to walk the tree and print out the values stored in the B tree. So in our page format, the header is followed by an array of offsets. Okay, so here's where we, where it's like, why does this end on with these last 2 bytes, and there's 2 free bytes in the rest of that word. So each entry in the array is 2 bytes, and it gives an offset at which the entry can be found. Each offset is specified by using a base of HF offset. Okay, so it is like reading from the end. Is it not? Means offset 0 will be greater than offsets 1 as the first key written goes to the very end of the page. That's really curious to me because I would think that if you're writing this algorithm, it would be easier. There's got to be some performance reason for this, because I would think it would be easier to have the smaller thing at the beginning of the page rather than at the end of the page. Interesting. Okay, so then it's like you take HF offset and you add, which is 16 bits, you add each of these offsets. So I guess there's going to be n entry offsets. Oh, okay. So it's like they allocate the offsets and then they write it in reverse order. Okay, so this is a gap. So it's saying there's 300 bytes that are offsets and entries in this first page, this internal node type 3. Okay, so so it sounds like what we're going to have is a loop to collect the offsets. Can be quite helpful to extend your code which prints the header format to include the offsets array and a hex dump from HF's offset until the end of the page. Okay. So okay, so let's look at what they have to say. Extend your code to read the same test data file, and starting from the root page, walk the pages pointed to by internal entries in order, and read out each key and value. Okay, let's look at their example output. So they print page 0, page 1, and these are the offsets. I'm guessing that's supposed to be an array. Offset 288, offset 216, offset 0. Did ours print there were only 3 entries? Yep. And then it prints the data. Okay. We might need to do something like that. Page 2 reads the offsets, right? The date. This is all leaf nodes. There's page 3, leaf nodes again. Page 4. Okay, and then it goes key value, etc. Okay. I don't want to do this whole hex dump thing. I think that's kind of obnoxious. There are programs to do that for us. I don't want to do that. But what we could do is add the offsets. Yeah, so let's make a new field in here is offsets. And that's going to be a vec of U16, right? And what we're going to do is go offsets. We're going to do some functional style. And we're going to map over that. Just call E for entry. What we're going to do is do U16 from LE bytes page, and this is going to be it's going to start at page 26, or it's going to start at 26. Yeah, 26 plus, we need 2 bytes, 2 times E, right? To 26. Well, they're 2 bytes each, so we can do 28 plus 2 times E. And then try into unwrap, collect. Whew, that was an expression. Okay, so what's wrong here? Oh, I need to convert this into a U size. And then that expression will be correct. Okay, and then we'll put offsets in there. And let's start with that, and then we can see if we get out the right numbers. I don't want to print out this data. What we'll do later is outside this loop through the offsets and adding the HF offset and read those things. Okay, so let's make sure that the offsets are correct on all of these based on their sample output. Did I do LE bytes? Because I'm wondering if because that doesn't look right. Oh, I need to subtract this from it. Okay. And we'll subtract HF offset. Let's see if that produces the same output. That's looking better already. Yeah, okay. So interestingly, that's kind of an absolute offset. I don't know why the HF offset is necessary to, I guess that's for internal bookkeeping, but those offsets are actually absolute, which is really interesting to me. Yeah, so 288 plus 3796 is going to be 4084. So uh, 12 bytes. Okay. So that's good. Now we can go here. What we want to do is print out this, right? Key value. So let's look at representing the other types of nodes, and then we can probably end the stream there. Okay. So the entry formats. Make a new struct. So there's key data entry, internal entry, and overflow entry. So key data entry, and we're going to have internal entry, and we're going to have overflow entry. Now, part of me wants to make this an enum because it's got this type discriminant in there. We know that we have to read this. Maybe let's do let's say enum entry, and yeah, let's make it key data, and it's going to be a struct internal overflow, and then okay, so in a leaf page, the first one is the key off, and the second one is the value. So, okay, so this is going to be length is going to be U16. We know the type, and the data is going to be a vec U8. Or maybe let's say it's a slice. Here. Because we don't want to allocate vecs for silly reasons. Okay, so an overflow entry. This page type and delete flag. This is so weird. What is this? I don't know what the delete flag is. It's not saying. Okay, so page no is a U16, and tlen is a U6 U30. No, these are both U32s. Yep. Okay. Let's look at internal and then see if we can this is page type and delete flag. This is so weird. Like, it's saying key data entry is 1, but these others are based on the page they're in. That's kind of weird. And I don't know what the delete flag is, like if that's like flipping one bit of that U8. I'm not sure. So page number is a U32, and Rex is a U32, and then data is another slice. Okay. I'm not sure that we're going to encounter these two based on what the contents of this file is, because we haven't made modifications to it. We've only created it, right? Like it hasn't had deletions or rewrites of keys. So I think that we're going to not encounter these other nodes, which is interesting. So I think probably what we'll do now, you know, it might be interesting later. Sorry, I keep digressing. We made these constructors sort of like new or whatever. It might be interesting to say, make this a try from, a slice. And we could do the same with the metadata. But maybe that's an exercise for making a nicer internal API. For now, I just want to get the data out. So let's Okay, we're going to do new, and we're going to give a, this is going to be an entry, which is going to be a slice of U8. And obviously it needs to be at least 3 bytes long. And this will return self. Okay, so this needs to be tick A here as well. So if entry.len, and I don't know, maybe I want to call it buffer because it's not a full page. We don't know if it's an entry yet. Less than 3, panic, invalid, entry, length. I'm just being a little bit paranoid here with the panics. Bear with me. Okay, so what we want to look at is let's match on buffer 2. And yep. And if we see that it is 1, then we know we have a key data entry. So length is going to be, here we go with that stuff again, from LE bytes, buffer 0.2, trying to unwrap, okay. And then the data is going to be and for now I'm just going to do unimplemented on that branch because we don't care about it. That's going to be slice from byte 3 to the end. Okay, so it's saying that's not used. All right, so what maybe I'll do now is so we have the header, we're printing it out. This is not, our output is not going to look exactly like theirs because I'm not printing this goop. What I'd like to do is say if header dot ty, this is where it might be good to have some either like constants or something for these things, as well as for matching on. Like an enum would be the ideal thing here. I don't want to go to all that trouble of trying to implement from or try from for that. Maybe what we'll do is we'll say const. What did they say up here? We have to go back. Okay, so meta U8 is 9. Let's say meta type, or type, let's call it type meta. Type internal 3 type leaf 5. Okay, and then we'll do type meta, type internal, and then we can use these constants later in the program. Self. Okay. So if it's a leaf node, a leaf page, then yeah, fine. If it's a leaf page, then we want to loop through the constants. The offsets. For offset in offsets. Header.offsets. Let's just borrow that. Okay. So we want to go okay, if it's a leaf, it's being key value data, right? So we can do chunks of 2. So we can do pair in chunks of 2. Okay, so we'll say let key offset pair 0, let value offset pair 1. And then we're going to say plus header.href offset because we subtracted it up here when we were constructing that, just so it would come out the same. I don't know if that's valid, but we have to add it back, right? Let's rename that to page. Okay. So, and then we have to add that as well. So let's do key, and this is we're going to have to do something here. Sorry, it just came to me. So what we need to do is make sure that we're not going to read. Oops, put that inside. Read any more than the length of it, because we don't know right here. We only know the offset. We don't know how long the thing is. So what we want to do here is make sure that we don't, like I was assuming, yeah, let's just get the buffer and like it's the entire buffer. but the header format is only giving us offsets, not the length of each entry. But the length is the first 2 bytes of that entry. So what we should do is have the entry be responsible for slicing the data such that it only has the length of of what was specified in the entry, right? Okay, so we're going to do so key. We will take is going to be entry new, and we're going to take the page, and we're going to say key offset, right? And we'll do the same. Notice how nice that is for the value offset. And this will be value. And then we're going to I'm not going to do it the same as they do. We're going to do key is key value is value, and just print the debug of them. Okay, so what's wrong here? Entry does not implement debug. Okay, so we're going to have to convert this to, or we're going to have to coerce this to usize, right? That's just easier right there. And we know it won't overflow. So what's wrong here? Arguments to this function are incorrect. Do we need to borrow again? Oops. Yes, we do. Okay. So page is, yeah. We just need to make sure we borrow. All right, let's see what we get here. This should be interesting. Now, it's going to print out the individual bytes because I'm not interpreting these as strings as their program is. Now, I could do something with like cstr. Or let's see, stir. I mean, we kind of know it's ASCII at this point, but if we want to make a resilient program later, it's going to be bad. There's probably a try from bytes. Try from a slice of U8. This is one of the leaky parts of C code, right? Okay, so we're just going to print out the bytes. It's going to be a bit ugly. If you know your ASCII key code, your ASCII codes, then you're fine here. Okay. Right. So we are getting. So length 20, length 20, length 40. So what they did here, remember in the original program, is, you know, this loop from 1 to 20. So every entry is at least 20 bytes long, and then they're, you know, making it only letters, right? So we know the first entry is going to be 20, the second entry is going to be 40, 60, and so on. And then on the last page, right, we're getting up there in size. So we have 380 is the longest one. Okay, that's pretty good. Key value, yep. So I think that's a pretty good place to stop. I would love to do this in Elixir as well. Maybe we'll do that next time for fun. What we'll be looking at after the entry format. So we didn't technically do this as they said. They say, like, have some kind of idea of a page that is beyond just the header. And maybe what we could do is say, make a page idea, which is an enum, which is either a metadata page or a B tree page, and then in that page hold the slice of the data that we're reading, and then have some methods that we can do this sort of thing. So they do it recursively, right? That's kind of, pseudocode. Weird. Okay. And then on the next one, what they're doing is trying to make a C compatible ABI with this. I think that's probably a bad idea for us on this stream. So I'm not going to do that. But I think, we learned a lot. Like there's, it's interesting parsing this file format. I would love to kind of have it be a bit more declarative, like being able to say that, and maybe we'll look into some crates next time. I didn't research it very carefully, but we could look into, well, can you automatically extract all these things for me? And then I'll provide sort of like Serday, right? Maybe even Serday is the answer. I don't know. But we could look into how to extract this stuff automatically. And we could do less of this, right? Yeah. Okay. So I think it's a good place to stop. If you have any questions, of course, drop them in the chat, and I will push this up to GitHub probably on the next stream. I don't think today is the time. But we'll probably resume this next week. So thank you for coming. Great to see those of you who are coming back, and old friends, of course. John, great to see you if you're still here. And I'll see you next week. Thanks.